Hello, this session is the second exercise of the hydrology video tutorial. We developed a hydrological model using the soil moisture method in the first exercise. We added the rivers, catchments, runoff infiltration links, and stream flow gauges. We characterized the catchments by entering area, climate, and land cover classes. We created key assumptions to manage the hydrological parameters and assigned them to each catchment. In this exercise, we will see how to use the WEAP Model Inspector tool to calibrate the hydrological model developed in the exercise 1. The tool has embedded macros to exchange information with WEAP. It is recommended to have followed all the sessions of the hydrology video tutorial sequentially. You will need to download the O8 hydrology folder to follow this exercise. In the exercise 1, we developed this model. We were exploring the results by comparing the observed versus simulated stream flow. Once we have completed the hydrological model, before using it to build scenarios or assess the available water resources, we must calibrate and validate the model. We will use the WEAP Model Inspector tool. Before using the tool, we need to open the complete hydrologic model version of the SEI Tutorial Hydrology Exercise 1 model. If you have WEAP in other languages rather than English, you must change it to English. The WEAP language must be in English because the macro codes uses the name in English of the WEAP elements, variables, and results. We need to enable the macros in the WEAP Model Inspector tutorial file. We will follow these 5 steps to use the tool. First, we need to modify the hydrological parameters in the tool, not in WEAP. Second, execute the macros by clicking on the Run WEAP button. The run time depends on your computing capacity. Third, verify the streamflow graphs and goodness of fit metrics. The graphs should be used to understand the hydrological response to changes in the parameters. For example, if the peak flows increase or decrease, if the base flow increases, if the response is slower or faster. The tool can run in batch. The end set of parameters are constructed by generating random numbers between a minimum and maximum value for each parameter. Fifth, choose the best set of parameters based on goodness of fit metrics and water balance results. Remember that the tool is not general. Modifications must be made in macros, graphs, and formulas to couple the tool with a different model. The tool was already modified to work on the SEI Tutorial Hydrology Exercise 1 model. In WEAP, go to Area, revert to Version, and open the complete hydrologic model version. We have the model opened and the tool ready to use. The instructions to use the tool are in this sheet. In the main sheet, you will find the list of the hydrological parameters created in the SEI Tutorial Hydrology Exercise 1 model. The hydrological parameters are controlled by key assumptions. You can change these key assumption values from this tool via macros. For example, change deep conductivity from 228 to 150. Click on Run WEAP. The tool starts assigning these values to the key assumptions in WEAP. Then the model will be run and the tool will import the results. When the macro finishes, a pop-up window will appear. You can assess the model performance for the last run in this section. The tool displays these graphs comparing the observed and the simulated stream flow and the goodness of fit metrics for the calibration and validation period. The Nash index, the root mean squared error, the bias, and the correlation coefficient are shown. You can modify the tool and include other goodness of fit metrics. Regarding the Nash index and correlation coefficient, the closer to 1, the better the model performance. Meanwhile, the bias and the root mean squared error, the closer to 0, the better the model performance. We can see on these graphs how well the model represents the observed stream flow. The time series, the annual cycles, and the scatter plot are shown. In this case, we use the split sample test. We split the modeling period into two, 1990 to 2007 and 2008 to 2015. Each time the tool runs, the list of the parameters and the goodness of fit metrics results are saved in the previous run results sheet. The tool was used previously 550 times. We just run it one more time, and now we see 551 records. For example, change the water capacity from 2,628 to 3,500 and run the tool again. Click on the Run WEAP button. We will have 552 runs. The tool is useful to evaluate the hydrological response due to parameter changes. We can run the tool in batch. We will test 5 sets of parameters using this feature. Go to the main sheet. We will use the G and H columns. First, in the H17 cell, we need to set the number of runs, in this case 5. Next, we set the minimum and maximum values to define the interval at which random numbers will be generated for each parameter in the list. Click on the Create a Random Set button. The tool generates random values for each parameter in the batch runs sheet. It will appear in a pop-up window. New parameter set created. Use the Test Trials in Batch button to run all the combinations. Accept. Click on the Test Trials in Batch button. The run time depends on the number of runs, the complexity of the model, and the computer capacity. Each row represents a set of parameters. The tool starts assigning those values to the key assumptions in batch. When it finishes, we can check in the previous run results that there are 5 more records. We have the results from 557 runs. The advantage of having the goodness of fit metrics for several sets of parameters is to evaluate which sets meet the performance criteria. Go to the model sensitivity sheet. We use this sheet to organize the previous results in a table and apply the performance criteria to the results so that we filter the sets of parameters. The filter results are based on the table. After running the model, you must update the table first. Then you can apply the filters. Click on the One Generate Table button. The tool may display a warning indicating that a sheet will be deleted. This is related to the code and is normal. Click on the Delete option. We can now apply the filters. We are going to get the sets of parameters that meet these performance criteria. The Nash index in calibration and validation will be greater than 0.5, and the absolute value of the bias index will be lower than 10%. Click on the To Apply Filters and Get Results button. As we see, some sets of parameters meet this condition. You can change the performance criteria varying these values. Next, you will have to apply the filter and get the results. This graph shows the values of the sets of parameters that meet the performance criteria. The first graph shows the interval of the parameters. The second one shows the minimum and maximum standardized values with the mean. Shorter bars will show the most sensitive parameters. The third one is a box plot of the goodness of fit metrics. As you can see, the tool is useful to calibrate and validate the model systematically. You can vary the hydrological parameters and evaluate the performance of the model. You can continue exploring the tool, aiming to improve the performance of this model. The model is calibrated and validated when you find a parameter set that represents the water balance in the study area. The simulated streamflow represents the observed streamflow, and the goodness of fit metrics meet the performance criteria. You can rerun the tool using the best set of parameters found so far. We could use the PRR simplified sheet. This is the generated table. Filter the parameter sets that meet the performance criteria. Copy and paste the values and run the tool again. Remember that this tool has been adapted for the hydrological model developed in the exercise 1. It is not a general tool. If you want to use it in your own models, modifications must be made in macros, graphs, and formulas. We have developed in R a general tool similar to the Model Inspector tool. It can be used not only to assist the calibration and validation process of a hydrological model developed in WEAP, but also to run a WEAP ensemble. Calibration results can be explored for each run. Observed versus simulated streamflow, water balance components, and goodness of fit metrics. Each tab of the tool contains instructions.